discussion. To make it a bit more structured, I think it's good to we have 2 prepared questions, and then we have a short statement from each of you, and then we have some back and forth towards that. And I think, Martina, you can start with the first question, and then we go first with the hybrid. So Andrea first, then we go to Carolyn, Rika, and so forth. We are back, and then we go to the next. Yeah, let's see how this works.
Okay, thank you, and thanks you all for being here. So the first question we wanted to talk about is, what do you think that are the main challenges and bottlenecks for achieving good performance in the manipulation of deformable objects? So maybe, Andrea, if you can start talking about this.
Yes, thank you. So thank you also for letting me speak first. So yeah, it's a very I would say broad question, because the field itself is broad, so it's hard to I think this comes out regularly at these meetings. There is so many different things we consider as deformable objects and different approaches. So well, I usually don't self-cite, but we did write a paper a few years ago. I think it came out in 21, which was a follow-up of a similar workshop, and it was on RAM, and we mentioned, in fact, the challenges and methodologies which should be addressed by newcomers in the field. And I think well, of course, that paper came out on IEEE RAM, and I recommend it. But my personal opinion, is I think perception is crucial, and of course modeling, which comes along. I think nowadays it's really very difficult to have this perception modeling running online at interaction time, so that the robot can operate immediately on the object. But again, it's very, very, there are other things as well. For example, the grippers and the hardware we have are not good for certain tasks. It really depends on the tasks, but we should have better touch sensing. So now there's a lot of buzz, and I think it's very nice with the gel site type of tactile sensing, which are cheap and seem to be very performing. Maybe that's also a good tool for manipulating soft objects. Yeah, that's my 2 cents.
Okay, that's great. Thank you. So maybe we can keep moving to the speakers that are in person. So Michael, maybe you can moderate now.
Let's just go. Right, we start with Carolyn, and then we go this order.
Okay, yeah. So I think the question touched on what are some bottlenecks in this area, and I would say that I think there's a microphone there. Or should I just pass around? Oh.
Yeah, try passing that around.
Okay.
But the audio is fine.
Okay.
What for the room?
So,
Okay.
So in terms of bottlenecks, I would say that the more complex of an object, like when we start looking at doughs, for instance, or granular materials, right? How do we find a good representation that kind of succinctly summarizes what we need to know about that material or object that allows us to accomplish whatever the goal task we want to do? How do we deal with such high dimensional representations and dynamics, right? I think figuring out how to represent those succinctly and efficiently is kind of where I see the bottleneck right now. And I think a lot of people touched on this today.
I think one of the challenges we have is figuring out if we do want to learn from simulation and how much is really the center gap manageable in this sense. So it seems that the rigid in the world of the rigid bodies people know very well, their biggest enemies, the contexts through which they cannot differentiate, that create, chaotic behavior and so on. And it would seem at first glance that we have it easier in the deformable world, right? Because maybe the context is softer, but it is still unclear whether we benefit enough because our models would have to be necessarily harder. So I think that's kind of one of the big challenges to understand in the kind of time of the big data and being able to collect a large data. Should we go more in the learning from real data, collecting large data sets, building large models from real data, or should we push on more on making the simulators usable and learning from that and so on? So I think that's kind of one of the challenges that we had. Very like robust simulators that have very small, like a manageable sectorial gap that maybe we could make in faster progress.
Yeah, I think in deformable object manipulation, there are so many challenges. It's like really hard to pick one. But I think one thing that really bothers me a lot, what I think a lot about, is what is supposed to be the right state representation. I think it's independent from the method that we take. Like if we want to define a task in deformable object manipulation, you need to define the goal state. So how we actually even define the goal state. And I think right now, what we mostly see is that we kind of choose different representation based on different object we manipulate, based on different tasks we are trying to do. And is there a way that we can unify it? Is there a representation that can be like unified, applied for any objects or tasks? Yeah.
I definitely agree with that last point a lot. I think that particularly in my application spaces, what does it mean to succeed? What is a reward? Where do we get these values when we're talking about complex tasks that people spend decades learning to perform, and the right way to perform is one of the things that I think about a lot. And then also more complex modeling or inferring kind of environmental reaction or interactions outside of just the deformable object you're manipulating. So ways in which it's adhering or adhesion to, the ways in which it adheres, there we go, thanks. My PhD is not in English. So, modeling these, overcoming these, accounting for these in safe ways is one of the things that I think.
So I agree also. I think what Carolyn and Shuran are pointing out is the complexity of state in this environment. I think it relates to this issue of reset that I think we all struggle with, because we want to try experiments and getting back to the same initial state is very difficult, so that it's hard to compare performance in many of these contexts. The one thing that I just walked past the compliant motion manipulation workshop, and I think compliance is really important here, because when I think about how I manipulate many of these soft objects, I'm using some sort of compliance. I'm not really, for example, with dough or granular material, I'm not actually ever really knowing the state of all the different objects or components, but I'm scooping my hands in such a way that they force the objects to comply with my hand surfaces. So understanding that in some way, it may be really important, because we may not need to know the precise state of the system, but we can impose constraints such that the state has to conform to what we're looking for.
Yeah, I'm really happy you all brought up the idea of representation, because these objects are so complex. We tend to err on the side of the more quantities that are captured, the better. But that gets me thinking a lot about speed and the usability of these simulators that we all basically work with. And so, for example, like we can't really use online deformable prediction right now. Simulators that are accurate are slow, and at the same time, if you want to train these surrogate models, we need a lot of data, but to collect a lot of data, you also need speed. But it's kind of a circular problem, because if those, let's say, for example, FEM solvers were really fast to begin with, then we wouldn't need to collect that much data. So it's kind of a problem of anticipating, what should be solved first? Do we wait for compute to catch up, or do we pour an effort into data and training to kind of solve the speed issue?
Right, thank you very much. Now we have the chance to add something. Now you have heard other panelists speak. Maybe you want to add something to your original answer. If not, we move on to the second question. Additional insights? No takers?
May I ask a follow-up question?
Yes.
Okay,
please.
so we all know that deformable object is so hard. But is there some like good aspect of it? Is any aspect of deformable object actually easy, or we actually solve like anything that we can think about?
It's funny you say that, because I was just thinking, one thing that really we get for free is grasping. Grasping is really easy. I mean, it's you know, if you put a stuffed animal in front of a robot, grasping that is completely trivial, right? So you can impress visitors that way too. Just put a stuffed animal on, the robot will pick it up and they'll go, wow. But it's so easy because of natural compliance. So grasping is one. I don't know, others, benefits?
Just go all the way.
I just want to counter that one. Isabella did show that grasping tofu is hard though. So there definitely are categories where grasping is a lot easier. Like at Toyota Research, right now our challenge on my team, on the mobile manipulation team, our challenge task is to grab things off the shelf and shop for, help a shopper out, go to a grocery store and grab random things off the shelf. And some of the easiest things to grab are bags because you just go in and crush them.
Yeah, that's true. Bananas.
Who
should answer?
Yeah.
As you know, I'm your quintessential academic, so I will take that approach, but I have the following observations. Number one, this is completely at the beginning. You know, we really are just testing the waters, how to deal with the compliant objects. However, academically, if you go, and my colleague Ken is here, go to the mechanical engineering department.
Sorry, can you just join the panel?
Oh, sure. You can find our colleagues in mechanical engineering department who wrote whole books on continuous mechanics and deformation and elasticity and all that falls into that. Now, it seems to me that one of the things have to be done here is to have students to learn maybe the whole book of continuous mechanics, but certainly the principles that the mechanical engineers and mechanicists have developed over the 200 years. This is really not new for them. So that's number one. So then, given that we go through that exercise, what is obvious to me, and Caroline showed that very nicely, we need better observables, measurements. I mean, she developed together with other students, Isabella in particular, this tactile sensor, but there are many variations of that. And the question is, what is an ideal observation system that we can measure easily, quite quickly, repeatably, the measurements of the stiffness. Now, finally, I would say that to put all this together as again, the mechanical engineers have the finite elements system as their Bible. I mean, you know, so there are software packages and all that. So the question from application, and Professor Tucker made a very strong point on that, is speed. How do we can compute this whole thing fast? Because I don't want to be under a robotic surgery for 1 hour when the machine computes how to do the surgery. So those are my comments. Thank you.
Yep, thank you very much. Is there some comment to the comments? Or we move to the next question.
May I say something?
Absolutely.
Ah, okay. No, I just have a comment a bit provocative about this unique representation. I think someone mentioned it. So I'm a bit, sometimes I'm a bit skeptical about this because I feel like maybe what we are doing, most works are application driven, and it's such a broad field to my, in my opinion, that it's probably, I mean, I understand that some methods should be transferred, but targeting a unique representation to me seems like a utopia. It's like if you replace the non-rigid in your workshop title with rigid, robotic manipulation has so many different perspectives. Just look at the parallel sessions we have at ICRA or IROS conference, because you can have in-hand manipulation, you can address pick and place, you can address compliant manipulation, so many different things. And for each of these, we are still struggling to find the benchmarks and challenges, or I mean, by challenge, I mean like the DARPA challenges. You know, Amazon came up with one format, but it was very specific for the pick and place. So yeah, unique representation maybe should be mechanical, but even the mechanical, if you deal with strings or fabric or you know, it's very variegate. So I'm just not too convinced about this, but that's my opinion.
Thank you very much. I think we can move on to the next question. Martina, if you like.
Yeah, thank you. So thanks also, Andrea, for this last comment. That's true for sure. And the next question is, what is the state of current simulators for deformable objects, and what features do you think are currently lacking? So maybe we can start again from you, Andrea, if you don't mind.
No, I don't mind, but unfortunately, I don't have a neat answer for this because I haven't worked with simulators so much, as you saw. So now we work a bit with SOFA, which we just started with. So it's a mechanical simulator, but I don't feel too aware enough, knowledgeable enough to reply on this. I would say we basically, generally, we work offline with the images we acquire from objects because we do a lot of vision-based work. So we don't really trust the simulators for what we have to do, which is maybe a mistake. So that's all.
Okay, thank you. So maybe we can switch to the in-person speakers. So Michael.
So it's been a little bit since I've worked with the simulator. The last simulator I worked with was Isaac Sim, which Rika and Isabella presented work on. And so obviously it's gotten a lot better since I've worked on it. But I would say one thing that I would love to see with simulators, like an advanced deformable object simulator, is being able to simulate more complex material properties, like for instance, stickiness. Like, I don't know anything out there that has that capability yet, or time varying properties, right? Like, I'm just thinking of dough again here. Like, if you let it sit, it's going to become more malleable. Like, how do we simulate that, right? And yeah, even representations in simulation, like if we cut a piece of dough in half, how do we know that's like the same piece, but now separate entities, right? Like, I think those are all interesting questions to ask.
So I work more with the simulators on the speed side, so, you know, training from large scale simulation. And for that, I was pleasantly impressed with Matl, actually, from which we built, you know, one of our frameworks that I talked about today. It handled, you know, underneath it has, you know, two different deformation, like generic deformation models, one of which is FAM, and you can make it reasonably fast. So not maybe as fast as you can do, real-time MVC with it, but definitely as fast as you can collect thousands and thousands and maybe millions of like data points for your learning algorithms. So on that side, I think we're good, and especially with Isaac Jim incorporating and hopefully releasing into the wild more of the deformable properties and deformable models as well. Now, the issue is that I think there is a difference between that mode, where we're interested in reinforcement learning, like large-scale learning from simulation, and the mode which is more close to what we need in robotics, where I'm dealing with a particular object. I want to simulate this particular object. And for that, probably the simulators are pretty slow unless you go to the high precision ones, unless you give up on the precision. And so this is something that I think was mentioned also before when we were talking last year in different workshops, that what we don't currently have with simulators is it's not like we don't have fast simulators. We have fast simulators, but they're not precise. We also have precise simulators. But what we don't have is a very flexible way to go from one to the other without really digging into the internals of the simulator, which takes up a lot of time. So I think if we spend a little bit of time kind of as a community to figuring out how to make the user interface such that you can say, here is the knob, I really want precision, and here is exactly how slow I expect this to be. But within the same simulator, I can turn that knob down and I will get speed. And this is something that would be nice. Currently, we have this, but we have it in all different kinds of simulators, so you have to switch between them to get this different modes.
Yeah, I think that's a really good idea. I want that too. And I think it can be used in different stages of training, right? For example, in the beginning, we can use the fast one and get more diverse training data. And then in the later one, we can actually use more precise one to do sim-to-real adaptation. Yeah, I think if I want to say something else, I think I really don't expect that the physics simulator is able to simulate everything that I want, but I do hope that we can do a better job to describe the limitations of simulator in a way to the end user or to researchers. I feel oftentimes we kind of discover the limitation of the simulator while we are doing a research project or in the middle of doing a research project. And I kind of feel like this idea of like from computer vision or like just in general, like creating a data sheet for your data set, like describing the limitations of your simulator, like kind of in a clear way or easy to understand way, I think that would be really helpful.
So I'm sure I know the least about the existing simulators of anybody up here, but I can tell you what I want to see in my applications that I don't see in the ones that I've used at least, and those are complex materials, so multi-material, non-homogeneous things. Changing topologies, right? The ability to cut and to adhere and affix things to other things and still have it work. Piercing, suturing, things like this. So those may exist out there, but I haven't seen it tonight. So tell me if you have it. Tell me. I'd love to see it. But
yeah, so I think that it's great to see so much interest in simulation right now. I think that Mujoko, DeepMind's purchase of Mujoko was a very interesting moment because they're putting a lot of effort now into more realism. And again, the danger with simulators is that they appear very realistic, and it's very easy to fool the eye. And so we can convince ourselves, hey, this seems to work, but then it doesn't transfer. So I think that one of the factors is somehow capturing the uncertainty that's inherent in the motion. Maybe the non-determinism, because simulators are generally deterministic, and so we don't see that variation at all. But it would be nice if it could show you a range of outputs outcomes that might happen. Let's say if you provide an impact to a cable, whereas a range of places that it could fall or land. So capturing that, I think, would be really interesting. The speed, as Rujna said, I think is very critical. We do have lots of access now with the cloud to very fast computing clusters that can speed this up. I think, as Caroline said, the issue of time varying material properties is really interesting because in surgery, for example, you absolutely have that. So as soon as there's a manipulation, you immediately get edema and changes in blood flow, and so that changes the material properties. So surgeons somehow find a way, humans do, to on the fly adapt to the changes of the property of their materials. So it seems like there's something where we learn, there's some fundamental approach that's not so dependent on the material properties that we seem to use, and then we adapt it on the fly based on observation to what's happening. And you're absolutely right also about tactile, because if you think about people who are blind, their ability to manipulate is actually quite good. So that's something we're completely missing. And gel site hopefully will be a way, but gel site is interesting because it's not particularly tuned to deformable. It's very good for rigid. So that's another area that we'll have to struggle with. And the last thing I want to mention is this idea of competitions or benchmarks. That if we had some good benchmarks that we could all try and work toward and then compare against, would be very valuable. And I saw that the group from Carmen Torres and WPI are proposing this this competition next year, which I think is a really great idea.
Yeah, in terms of simulation, each one that exists has, their downsides, mostly that they're not super accurate. But I think we are in a very unique position right now. Simulators in the robotics community are really just starting to ramp up, and that's mostly due to the ability to accelerate using GPUs. But these simulators have existed for a long time. For example, in mechanical engineering, right? Phenomena such as adhesion, heterogeneous materials, time-varying materials, they can be simulated, but they're painfully slow. On the other hand, the graphics community has also worked independently on their version of simulators that might not be physically accurate, but are fast and look correct. And as I mentioned in my talk, there's just so many different metrics that we might be interested in when grasping deformables, and they're object dependent. So for example, the tofu, right? We could not simulate breakage in tofu or permanent deformation in tofu with our linear elastic model. And to my knowledge, neither do any of the existing robotic simulators. But if we could kind of have a plugin or a way to kind of switch up the model such that breakage is modeled, then maybe you trade off accuracy in other scenarios, that could be great. A good example that I can also think of that has actually been done in practice is the problem of interpenetration within many of these simulators where your mesh kind of, crosses contact and you can't separate them after the next time step, and that's not physically realistic. But Chungmin, who is Professor Goldberg's student, like for example, she has repurposed a backend that uses IPC, incremental potential contact, to then build up a robotic simulator that solves that issue of removing interpenetration, but perhaps add a bit of a trade-off for accuracy in some other ways. So I don't really envision like this totally generalizable, beautifully fast simulator in robotics that works for any situation, but I do hope that we can kind of pick and choose which physical quantities we care more about and kind of have our simulator be flexible to that based on different objects and different tasks within one environment. I can foresee a future where that might be realized, and I think that would be useful to all of us.
Well, I will say one thing, what to me this all suggests, we need very strong interdisciplinary groups attacking these problems, and you have been doing it, and I have been partially doing it. But I think that from educational point of view and from university point of view, the walls between departments are need to be removed. And so that it's very hard to think about in one PhD, like Isabella is, to deal with and know every outcome from the material scientist, from the mechanical engineer, from the user, and even chemist, because a lot of these materials are due to different chemistry, to really include all of that. But if she, and I am as guilty as anybody else, if I would have generated an environment of all these people then possibly she would have had an easier and much more generalized system as she has now. I mean, I'm very proud of what she has accomplished, but nevertheless, it really points to this thing that we in academia still are promoting individual accomplishments in individual fields, and these problems require much more breaking the walls.
Everyone. We do one last kind of round. I mean, first, if there is any comments to the comments. Let's do one final round, 20 to 30 seconds, each speaker. What do you want to emphasize the focus on for the future? Like, where should we go? What should we put in grant proposals? Where should the community move? Let's start with Andrea again.
In terms of I think the applications should be oriented by society, and we should not forget that this is our purpose. Other than publishing as much as we can, we should also solve useful problems. And that's one thing. So currently I would think medical maybe, or I saw a lot of things about fabric and clothes folding, and I think I ran out of time. Or
Thank you. 30 seconds. That was the most important part. So these parts are the ones that come out.
What is the 30 seconds?
Yeah, because then if you only have 30 seconds to answer, only the most important things make it through.
All right, I'll start my 30 seconds. Okay.
Go.
So for deformable objects, I think being able to perceive important properties, material properties, or dynamics of deformable objects is important. And I'm blanking now, so I'm just gonna pass on the
All right, I think we have an opportunity to benefit from high speed up that we get, GPUs, big compute resources. And I don't think that we as a community know as of now what it is that we want to invest it in. Is it like a big FEM simulator that would do a very precise thing? Is it some particular phenomenon that we want to model? So basically figure out how to make use of the larger compute resources that we might be able to have and get them, yeah.
Okay, I want to say something different. Okay, so I would say multi-model or multi-sensory learning. I would say that we have a lot of sensors out there now, and also we're kind of converging on the method as well, like all deep nets, right? So I think, yeah, it is a good time to actually consider like merging all different type of sensors. Yeah.
I guess I would say that we should start from the ground up, keeping kind of the human in the loop in mind at every step. So what are the data requirements? What's the burden on collecting that data? How do these things generalize to new tasks and new users and new environments and things like this, so that we keep that.
So I think this real to sim question is something that would be very interesting to make progress in. I think if we could, even if we had these great simulators that we're wishing for, we need to instantiate them for our materials. So if we could find ways to do that quickly and adapt them to new materials, that would be very valuable. And I think that benchmarks is also going to be just so important for advancing this area.
This is not something I have personal experience with, but something I've seen come up from others' works. That's the idea of differentiable simulators for deformable objects. I think that's a really exciting field because it's useful. You can actually optimize over inputs and do some useful control. And yeah, I just think that's an exciting thing to investigate as a